Hey guys, welcome to part 2 of our pole loading series. Today we're going to talk about the loads applied to poles that are caused by weather. If you haven't watched part 1, I would recommend doing that before watching part 2. In part 1, we looked at 3 classes of 50-foot poles, and we evaluated the horizontal and vertical loads applied to poles caused by 4 different types of construction. We compared these loads to the maximum allowable limits for pole tip loading and bending moments. Just a reminder, the maximum allowable tip load is simply the maximum vertical load the pole can support if it was applied at the tip of the pole. The horizontal loads applied to the pole are converted to bending moments with respect to the ground line. Our first example was the load applied to a pole due to equipment. We found that a 3-phase transformer bank created a tip load of about 1,450 pounds and a bending moment of about 3,700 foot-pounds. Second, we looked at a tangent pole and determined a vertical tip load of 594 pounds caused by the weight of the conductors with no bending moment. Our angle pole initially created a large bending moment, which we then offset with a down guy and anchor. The tension in the down guy resulted in a vertical tip load of over 2,100 pounds. Lastly, we saw the same thing with our dead-end pole. The bending moment created by the conductors was offset with a down guy, the tension of which created a vertical tip load of over 3,100 pounds. With a couple of exceptions we covered in part 1, almost all horizontal loads caused by the conductors should be offset with a down guy and anchor, resulting in a total bending moment of 0. Why then is the maximum allowable bending moment of a pole important? It's because of this. When the wind blows like that, it can create a huge amount of horizontal force, as the wind pushes not only on the conductors, but on the entire pole itself in a direction perpendicular to the line. If the maximum bending moment of the pole is exceeded by these forces, it can cause the pole to break or topple over. This can also cause a cascading effect that may cause the adjacent poles to go along for the ride. Because of this, it's critical to ensure that pole lines are modeled to withstand the effects of wind and weather. Exactly how much wind utility poles need to be designed to withstand has been outlined in the National Electric Safety Code. The NESC has divided the U.S. into 3 primary loading districts, based on the expected wind and weather conditions over time. They've created heavy, medium, and light loading districts, each with different design parameters that poles installed in these districts should be modeled to withstand. For example, a pole installed in the medium loading district should be designed to withstand temperatures down to 15 degrees Fahrenheit, a radial thickness of ice buildup on the conductors of 1/4 inch, and a horizontal wind pressure of 4 pounds per square foot. There are also NESC extreme conditions that apply to poles over 60 feet above ground. If you're in California, CPUC General Order 95 provides slightly different weather conditions, and your local utility may have additional weather cases due to known local conditions. A pole line needs to be designed to withstand all of the weather cases that may apply. Let's look at an example to see how these values are applied. Let's assume we're evaluating the same tangent pole we looked at in part 1. This pole is installed in a light loading district. According to the NESC, we need to assure our pole can withstand a temperature down to 30 degrees Fahrenheit with no ice loading and a wind pressure of 9 pounds per square foot. From part 1, our adjacent conductor spans were 200 feet and 300 feet. The weather span that we want to evaluate consists of 1/2 of each of these adjacent spans. This is the same as the loading span we determined in Part 1. So our weather span consists of the 4 conductors located within this 250-foot rectangle. We need to determine how much force the wind is applying to the conductors within our weather span. If you remember, our conductor was 336 ACSR with a diameter of 0.684 inches. The first thing we need to do is determine how much wind force is being applied to each conductor. This is easier than it sounds. We simply need to calculate the surface area of the cross-section of our conductors as if they were a flat surface. The height of the cross-section is simply the diameter of the conductor, 0.684. And the length is the length of our weather span, 250 feet. If we do the math, we end up with a cross-sectional area of 14.25 square feet per conductor. Since we have 4 conductors, our total surface area is 57 square feet. According to the NESC, in a light loading district, the wind applies a force of 9 pounds per square foot. If we multiply that by our 57 square feet, we end up with a total wind force of 513 pounds. Since that wind force on the conductors is being applied at a point on the pole that's 43 feet above the ground line, it creates a bending moment on the pole of just over 22,000 foot-pounds. We're not quite done yet, though. We still need to add the bending moment caused by the same wind being applied to the pole itself. To do so, we can use the values shown here. Being careful to determine the diameter of the pole at the ground line, we can calculate the cross-sectional surface area of our pole the same way we did for the conductors. Although don't forget, this area is shaped like a trapezoid. I'll let you do the math, but we end up with a cross-sectional area of about 35 square feet. Still using the same 9 pounds per square foot of wind pressure, we can now determine that the wind is applying a force of about 315 pounds to the pole. We can also determine the bending moment caused by the wind by applying this force to the geometric center of the pole. Again, I'll let you do the math, but that geometric center is right about here, at a point about 20 feet above the ground line. This causes an additional bending moment of about 6,300 foot-pounds due to the force of the wind on the pole. Let's summarize all of this real quick. In Part 1, we started with a 50-foot pole. We then installed a 3-phase transformer bank. This created a tip load equivalent of 1,451 pounds and caused a permanent bending moment of 3,710 foot-pounds. We then added a cross-arm and 4-wire 336 ACSR conductors, which added another 594 pounds of tip load, but didn't create any additional bending moment. Per NESC guidelines, we determined the effect of wind loading on the pole in a light loading district to be a combination of the wind on the conductors, which created a bending moment of 22,000 foot-pounds, and the wind on the pole, which added an additional 6,300 foot-pounds of bending moment. The total anticipated loading on our pole is 2,045 pounds of tip load, with a total bending moment of 32,069 foot-pounds. According to our pole loading chart, we would need our Class 3 pole to meet all of the loading requirements we've just determined. Let's do one more example. Let's assume we're evaluating the same tangent pole we just looked at. This time, we're in a medium loading district. According to the NESC, we need to assure our pole can withstand a temperature down to 15 degrees Fahrenheit, a radial ice load on the conductors of 1/4 inch, and a wind pressure of 4 pounds per square foot. The NESC also notes the weight of ice to be about 56 pounds per cubic foot. First, we'll look at the additional weight on the pole due to the ice on the conductors. We still have our same 250-foot weather span and the 4 336 ACSR conductors. We need to add the 1/4 inch of radial ice. It's not too difficult to determine that for every 1 foot of conductor, we have about 8.9 cubic inches of ice per foot of conductor. If we apply this to the 250-foot weather span and include all 4 conductors, we end up with about 5.1 cubic feet of ice. Using the weight of ice given in the NESC, we end up with an additional load of 288 pounds. Since the cross arms are attached 1 foot below the top of the pole, I'll multiply this by 0.93 to get a pole tip equivalent of 268 pounds. We'll then need to determine the new wind load on the conductors due to the additional mass of ice. To do that, we just need to determine the cross-sectional area of our conductors again, this time including the 1/4 inch of ice on both the top and bottom of the rectangle. This gives us a surface area height of 1.184 inches. We'll multiply that by our 250-foot weather span and include all 4 conductors. This results in a new total area of about 99 square feet of conductor surface within the weather span. After we apply the 4 pounds per square foot of wind pressure, we end up with a total wind force on the conductors of 396 pounds. Since that wind force on the conductors is being applied at a point on the pole that's 43 feet above the ground line, it creates a bending moment on the pole of just over 17,000 foot-pounds. Lastly, we need to determine the wind force on the pole and the corresponding bending moment. This is pretty easy since we've already done most of the work. Our cross-sectional area of the pole is still 35 square feet, but our wind pressure has changed to 4 pounds per square foot. This gives a total wind force of 140 pounds, and when applied to the geometric center of the pole, we end up with a bending moment of 2,800 foot-pounds. Just a moment ago, we looked at our results from the light loading analysis. Let's see how our medium loading results compare. The loads due to the 3-phase transformer and the weight of the cross-arm and conductors didn't change. The wind load applied to the conductors actually went down to 17,000 foot-pounds. This was due to the decrease in wind pressure from 9 pounds per square foot to 4 pounds per square foot. The wind load on the pole went down as well for the same reason, but we added 268 pounds of tip load due to the extra weight of the ice on the conductors. Our total tip load went up a bit as a result to 2,313 pounds, and the bending moment decreased to 23,538 foot-pounds. This is an example of how a change in the loading district will affect the results of a loading analysis. Pretty cool, huh? Here's an example of a pole installed in an extreme loading district. Because of the very high wind loads applied to the pole and the conductors in this area, wind guys have been installed on this pole. You can see them here. They've been installed to stabilize the pole from the forces applied in the transverse direction. Here's another one. This one has wind guys installed in both the transverse and longitudinal directions. This is also a Class H1 pole built to withstand the extreme wind and ice loading at the top of this mountain. 2 quick things before we conclude. The chart we've been looking at with the different loading values was created as an example. Be sure to refer to current standards within the NESC, the GO 95, and your local utility guidelines for more accurate information. Also, different types of overhead line construction have been categorized as different construction grades. These construction grades may require reductions in the allowable loading values based on a variety of factors. Be sure to understand what grade of construction your project falls under, so that strength and loading factors can be applied appropriately. There are also a handful of pole modeling software applications that do all of this and more. If you're looking to learn one of these, or you're just looking to expand your knowledge regarding overhead line construction, I hope this helped. Thanks for watching.